Next topic will be this self-supervised learning. So self-supervised learning is a kind of learning in which we don't have labels to learn. So we have input vectors and we want to learn something on those vectors, but without having any specific output to reproduce. Or we will have to fabricate this output from the labels themselves. Not from the labels, from the input vectors. So these are known as self-supervised tasks, and we have to generate pseudo labels from the data itself. And these are three typical approaches. So one of them is mask prediction. So we have to predict missing parts of the input. So for instance, masked pixels or words. We have to denoise the input data and reconstruct original data from a noisy version. So we have an input vector, we add the noise, and then we have to recover the first vector. And this is useful in anomaly detection. So when you have an instance, a vector from which you have a large reconstruction error, that means that very likely that instance is an outlier of your distribution. And one of the most typical is this autoencoding, where you have to learn compact representations of your input data. So you go through a bottleneck, a latent space that is much smaller than the input space, so that with that information in the latent space, you have to recover the input vector. So let's see each one of these. So these, for instance, generative self-supervision. So you have to predict what is the next token in a sequence. So you are given a set of words. Each one is a token in the sequence, and then you have to predict from this one. You have to predict the next token in the sequence. So that is the task that the network has to do. Then, for instance, these masked data self-supervision, where you have to predict a missing token, a missing phrase, a missing pixel. So there are here a couple of approaches. In one of them, we see the sentence here is Harry Potter is a series of fantasy novels written by J.K. Rowling. So we mask randomly parts of this sentence, and then the transformer or the neural network has to predict what is the most likely word that was missing in the mask. And here is a different approach in which the masks are not evenly distributed, but they come in bursts. So Harry Potter is, and then 3 masks in a row, and then 1 mask, and then 3 masks in a row. Then we have this contrastive self-supervision, in which you have one image, and then one image of one input vector. You do some augmentation, so the augmentation could be different parts of the same image and different transformations. So here you are also changing the colors and the zoom and so on. The same for many other examples. And then both of these images go through a neural network that produces some latent representation. This latent representation has to be such that 2 vectors coming from the same original image have to be closer to each other. Closer, it doesn't mean that they have to be the same, but they have to be closer than the representation of any other augmented image of any other object. So if you have any other object like here, and you have the representation, the latent representation of that latent representation has to be different from this one, has to be different from this one. So this is somehow related to the triplet laws that we also studied. We have these CMS networks. The idea is somehow the same. So you have two instances of the same label, although the vector is completely different, and then they have to be embedded into some encoding such that the Euclidean distance of that encoding makes them close. And here you have some example of how they will evolve. So at the beginning, while the network has not learned, they are all intermediates. But then as the network starts to learn, at some point it is able to distinguish the different digits in this dataset. Then we have these autoencoders. Autoencoders, they are used for data compression. And so let's say that you have an input vector, you go through an encoder, then the encoder has some low dimensional latent space representation that is supposed to have all the information needed to reproduce the original vector. And that reproduction is done by the decoder. So the decoder takes the latent space representation and tries to reproduce the input vector. So these are architecture of encoding decoding is very popular. And this architecture of autoencoding can be used for denoising. So let's say that we are given an input image, then that input image we add noise, and then this noisy version of the vector is the one that goes through the encoder-decoder architecture, and the output of the decoder is compared to the input image, and then there is a loss for the reconstruction, and this way this autoencoder architecture knows how to denoise input images. Autoencoders can be also used in a supervised mode, and they can be used for this data transformation. So this data transformation can be, you are given an input vector, this input vector goes through the encoder, then you have the latent space representation, and then you have the decoding. But the decoding is different from the input vector. It has to reproduce something else. So for instance, a mask, or they can be a higher resolution version of the input image. So or it can be a different orientation of the 3D input object. So these autoencoders for data transformation, you need the output so that you can compare the output of the decoder to the output that you want. Another variation of these data compression architectures, these autoencoders, are these variational autoencoders. So the variational autoencoders, they are represented in this way. So you have an input image, you have an encoder, but the encoder now, instead of encoding a fixed latent vector in the latent space, it predicts some mean and some standard deviation, and then there is a random sampling from a distribution. You have to fix the distribution. Typically it is the Gaussian. So from a Gaussian distribution you have to pick a random vector with this mean and this standard deviation, and that random vector has to be decoded to have to be similar to the input image. And this randomization here, typically it helps to generalize, so that you don't learn by heart the input data set, because there is a randomization step here, so that you learn features that help you to reproduce the input vectors. And there is a trick there to make the autoencoder, this variational autoencoder, to be differentiable. So this random step, so for instance here, if we have the mean and the standard deviation, and here we have a random a random draw from that distribution, that random draw would not be differentiable. So the trick typically is to make this mean, this standard deviation, and now your prediction is like this. So the set is mu, which is coming from this branch of the encoder, so that is differentiable. Sigma, that is also differentiable because it is given by the encoder, and then you multiply a random signal. So you have this random signal here that is coming in, and then the input. So this is another input, and you don't want to propagate the loss error from the output through this branch. So the propagation is performed through these two branches, the mu and sigma, but not the random noise. So now it is the back propagation is differentiable. So somehow this is represented here, and there are typically two kind of losses here. One is the reconstruction loss that you want to minimize. The other one is you want this latent space to be somehow have some nice properties. One of the nice properties that can be required is that this thing holds or is as small as possible. And the meaning of this is that the distribution of set has to be Gaussian. Or it is coming from a KL divergence from the distribution, the actual distribution, and a Gaussian. And we will see that in more detail in some mathematical details of the variational autoencoder in the next video. Yeah, so let's stop here.